journey of understanding deep learning with our pencil, okay? So this is deep learning by hand. Part 2, okay? I don't know, maybe I do a part 3 later on. But we already saw the gradient descent the other day. This is the process that creates the intelligence, okay, finding the minima of the functions there. But there is also a very clever process called convolution. Which makes it possible to shorten information and compact information and relevant information in the process of deep learning. And basically what it does, it takes a domain and gets the most relevant information out of it. So you have this image with its colors and everything. And imagine we want to recognize in the image some objects, okay? What convolution does, it takes and eliminates the non-relevant information and takes only the how do you say, the contour, the edges of the image. Okay. So we are able to identify the objects later on. And this happens in a very clever way that I will try to explain today. It's simple, but you need to see it 1 or 2 times. And once you have seen it, you will understand it's super easy. And it's basically this gradient descent and convolution are the backbone of what we call today deep learning. Okay, this is the reason why convolution is the reason why your phone is able to recognize your face and unlock it, okay? Because it recognizes certain lines and certain edges, and this leads to high-performing deep learning, okay? So the background, and of course, I will also give you some code. If you want to take the code and put it in Python, you can do it and play with it. Okay. So convolution is a technique used in image processing is the process of summing each element of the input image with its local neighbors. You remember when we explained the other day deep learning, we were talking about an eye, and all the pixels of the eye that are blue are together, and that's why we recognize the eye, right? Remember that maybe? If the pixels of the eye would be scattered in the image, not all the blues together, then you would not recognize an eye. You would just see a bunch of points, okay, random. Because there is this thing of a distance, because pictures are Euclidean, we can apply deep learning this way. Otherwise, we could not, okay? And that's why it's so difficult to apply deep learning to things that are not non-Euclidean domains like networks. Anyway, we have talked about that already. The convolution process uses some filters to extract the information we are interested in. We can use filters, convolution filters, to extract the edges of an image. We can use filters to extract the shape of an image, or to extract the texture of an image. So if it's raw, or if it's smooth. So using different filters, we extract different information from the data. Okay? So these filters are called, we will see now some of them. These filters are called something that comes from German, kernels. Okay? From kern, nucleus. So a kernel is, in this case, a matrix that shapes the weights of convolution. So let's take the image from above and talk about it a little bit in detail. Sorry. I want to have one image from photos. Let's take this one. Okay. And now we can take one detail of it. So we go and take this part, okay? And I want to crop it. And just skip the part I zoomed, I guess. Okay, something like that. Not really, not exactly, but you know, you can imagine. So from there we take the pixels, or we take the only this square, and we're going to talk about this. Okay. Okay. So the idea here is that each part of the image, this little square that we just painted, is in reality an m by n matrix of dimensions. Oh, not a matrix, in reality it's a tensor, okay? Of dimensions n times m times 3. Okay? Because you can recall from our lecture a couple of weeks ago, each one of these colors or pixels is in reality a superposition of 3 values, one red, one green, and one blue. You remember that, right? Huh? Yeah. RGB, B, G, R. So those are the 3 dimensions that we have, 3, and then N, and then M, or M and N. Okay? That's why we have, in reality, it's like a cube, if you want. We see only the color image, but in reality it's a cube. It's 3 layers. So, and each pixel that we see here, in reality is 3 values, a little vector, okay? A little vector, 137, 65, and 36. Something like that. This is R, G, and B. So what is an image? It's a bunch of vectors put together. And the distance between these vectors, it's important. The distance between the pixels, it's important. That's why we recognize the nose as red there, because all the red points are together. Okay? So the values are between 0 and 255. We talked about that already because of the 8-bit disposition. And I don't know, did I mention that? No. That the values, sorry, I did not mention that. The values of each channel are between 0 and 255. The reason for that is that each pixel is described by 8 bits. 1 byte is 8 bits. And each bit takes a value of 0 or 1. So the combination of zeros and 1 in 8 positions is 2 to the potent of 8, and that's 256 positions. That's why between 0 and 255. Okay? And that for each value. Yeah, so that's basically the basics, and now let's look into the kernels, okay? And let's explain what these kernels do. We get an input filter or kernel. So kernels can have many shapes and sizes. Let's say from 2012 to 2018, many researchers develop many ways to filter, okay? They develop different kernels, And that's the process you see of optimization of your iPhone. If you get better kernel, you get better information from the image, and then you can have, at some point, thank you, some face recognition. Okay? Servus. Okay? So the better the kernel, the better the face recognition process. The kernels make up filters which are a parameter in the convolutional layer. Basically, you need to describe how you extract the information from the image, and you do that by defining your kernel, okay? So there are kernels for attention, for blurring, to make your face unrecognizable. If you don't want a boy or a little kid to be in the image, you can blur it. For edge recognition, and I mean, there are very many. Whatever you can do with an image, you do it with a kernel. Let's look at some examples, and it will be quite intuitive, I think. So this kernel is called the corners kernel. And I'm just going to paint a 3x3 because it's kind of easier. Of course, it can be bigger or smaller. So our corner kernel looks like this. It has 1 and 1 there, -1 there, and then 0, 0, 0, 0, and 0. So this is an edge recognition kernel. Why? Because whatever it looks like, it will multiply by 0 what you're looking at, and it will only get, or multiply by 1, so leave it, or -1, leave it like exactly the way it is in the corners of the kernel. Okay? So let me write it so that it stays. This is an edge recognition kernel because only the edges, the corners, are non-zero. How do we apply it? It comes in the next slide. Okay. Now just look at the structure of the kernel. If we have a edge recognition kernel, we have zeros in the middle and ones or 0.8 or something weighted in the edges. Okay? So then let's look at an attention kernel. Attention kernel is a little bit different. So it has exactly the opposite structure. It has zeros in the corners, a big number in the middle, and -1 outside. So whatever you're looking at, you're going to highlight it. If I don't look at you, I am going to multiply you by 0, so you're gone. That's why it's called attention. I only pick what I'm looking at. Okay? So this is an attention kernel because the middle is highlighted. Okay, so multiplied by 4. But there is also stronger attention kernels. So 8 in the middle and then -1 everything else. So this is a stronger attention kernel because it multiplies it by 4. Okay? So these are just 3 examples. They are infinite. Okay? Infinite. You can have all sorts of variations, but this is just the basic. Any questions so far? Yeah.
How do we choose the correct kernel for the exercise?
Experience. So yeah, it takes time to train and yeah, so experience.
And the first one, the recognition, you only see, oh, there is something and there is something, but you don't pay attention on it. Right?
Yeah, now let me explain how it works, okay? I go into that right now. Good. So, okay, so imagine we have an image that is like this, like the one we saw here, okay? All right. Let me copy it. Let's make an example, okay, of how it works. So imagine you have that, a part of an image. Of course, you can have the whole image, but we go and we just take one little bit, okay, one tiny bit. So we can assume that it has 3 channels. So it's going to be R, G, and B. Okay. And now let me paint some numbers here that might represent these 3 channels. Okay, I'm not going to take the real values because That's for machines to do. I just want you to understand what is going on. So I'm going to take here the values, let's say, for the channel R, 1, 1, 0, 2, 1, 1, 2, 1, 1, 0, and 0, 1, 2, 1, 1, and maybe 1, 2, 2, 1, 1, and 1, 0, 0, 1, 0. So this is our channel R. This is this red mesh that we see there, okay? Just put the values there, from 0 to 255. And we have a channel G and we have a channel B, and if we put them together, we see the picture we have there. Quite easy, right? So now, how does convolution work? Let's define our kernel. What do you want it to be? A tension or something more fun? Let's say we take an attention kernel, okay? So we go and say it's going to be 0, 0, 4, 0, 0, minus 1, minus 1, minus 1, minus 1. This is our attention kernel. And now we apply convolution. We convolve. In mathematical terms, it's written like this: f convoluted with g to x. All right? Something you've probably seen. This equals f as a function of g applied to x. Okay? So this is the math behind it. How does it work to apply convolution? Now please pay attention to the thing there. And later on you can look at the video and then it will make sense, okay? So what you do is you take your kernel, and you apply it to this area. So we are going to multiply these two matrices. Dot multiplication of the matrices. Okay? And what we get is a number. So let's do the dot multiplication of the matrix. As I said, you have this in the video, so you can go and scroll back and forth and see how it happens, okay? This is why I do the videos. I think this is a better didactic way that give you a PowerPoint and go and say, go fuck yourselves with that, okay? It works better for your brain, so that's why I do it. So we apply the kernel to the 3x3 now, here. So what do? We say 1, 1, 0, 1, 2, 1, 0, 1, 2, convoluted with 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0. So as I said, this is our first thing, our first element of the convolution, and then This is our second, just a filter. And the convolution delivers a value which is 1 times 0, 1 times 0, it's a dot multiplication, okay, plus 1 times minus 1, plus 0 times 0, plus 1 times minus 1, plus 2 times 4, plus 1 times minus 1, plus 0 times 0, plus 1 times minus 1, plus 2 times 0. Okay? So I'm just multiplying each element to the 1 in there. So 1 times 0 is 1 times 0. Okay? 1 times minus 1 is 1 times minus 1. And so on. 0 times 0 is this. Okay? And we add it all. 1 times minus 1, 2 times 4, and so on and so forth. Okay? So as you see, this is super easy math. The most important value here is going to be the one in the middle. So this value of 2 is going to be highlighted. Whatever is there is going to be highlighted. The rest is going to be drifted down. Okay? So if you have a value there of a lot of green, it will go up. The green will go up. That's why in this filter that you saw in the beginning, I will show you the example later, I put a blue factor. If you change one number there and you put, instead of the blue filter, the red filter, you get the convoluted image becomes red. And people say, what the fuck? It's just one number, because you are instead of looking at one layer, you're looking at the next layer. Just changing, you know. If you understand the math behind, deep learning is not very difficult. Artificial intelligence becomes demystified. And all of a sudden you start being able to do it yourself and be creative, and it's so fucking cool. Okay, that's why I do it like this, super baby steps. I think it's the best way to learn it, instead of here showing you fancy stuff. I think this is the way to learn, okay? And to play a little bit with it. So let's do this math, okay? So in the exam, by the way, you need to do this, okay? So make sure you make some examples for yourself. 1 times 0 is 0, minus 1, minus 2, plus 8 is 6, minus 1 is 5, minus 1 is 4. Okay? So now what do we do next? We take the next pixel sequence. We go here. Okay? And we're just going to be sweeping all the image. So the next pixel sequence is 1, 0, 2. 2, 1, 1. 1, 2, 1. This is not a 0, this is the symbol of convolution, okay? Don't mistake it. And then the filter remains the same. Zero, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0. So I have 1 times 0, plus 0 times minus 1, plus 2 times 0, plus 2 times minus 1, plus 1 times 4 plus 1 times minus 1 plus 1 times 0 plus 2 times minus 1 plus 1 times 0. So that's 0 minus 2 plus 4 is 2 minus 1 is 1, and then minus 2 is minus 1. Okay, I go to the next 0. So now I take this 0 to 1. 1, 1, 0. 2, 1, 1. Notice that, oh, sorry. 1, 1, 0, 2, 1, 1. Notice that we are going every time we are moving our window one step. Okay? This is called padding. Padding. How many steps we move. We could also say we move 3 steps. This is a parameter that you need to adjust when you do deep learning. Okay? But I am just explaining now. Right now I'm explaining just the basics, so that's why please, if you know a little bit more than the others, apologies. So if you do that, 0 times 0 plus 2 times minus 1 plus 1 times 0 plus 1 times minus 1 plus 4 times 1 plus 0 times minus 1 plus 2 times 0 plus 1 times minus 1 plus 1 times 0 minus 2 minus 3 plus 1, 0. So from this first 3 calculations, the convoluted layer becomes, we already have our 3 first elements, 4, minus 1, and 0. Okay? So this 4 goes here, minus 1 there, and 0 there. Okay? So the same thing, we have done this for this, okay, in 3 steps. Now we go and do it for this. And it's just, you know, chunking matrices like. Let's do it, because it's important to be didactic. 1, 2, 1, 0, 1, 2, and 1, 2, 2. And again, the same filter. You cannot change the filter in one convolution process, okay? You have to do the same, use the same filter for all the image. Otherwise, you don't get nothing. So 1 times 0 plus 2 times minus 1 plus 1 times 0 plus 0 times minus 1 plus 4 times 1 plus 2 times minus 1 plus 2 times 1 times 0, 2 times minus 1 plus 2 times 0 equals minus 2, 2, 0, minus 2. So we have here minus 2. Straightforward math, okay? That's not really Let's continue. 2, 1, 1. 2, 1, 1. 1, 2, 1. And 2, 2, 1. Now 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0. So we get 2 times 0 plus 1 times minus 1 plus 1 times 0 plus 1 times minus 1 plus 2 times 4 plus 1 times minus 1 plus 2 times 0 plus 2 times minus 1 plus 1 times 0. Minus 1, minus 2, 2, 1, minus 1. And then 1, 1, 0. 2, 1, 1. 2, 1, 1. Convoluted with 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0. I mean, it's always the same. I hope you are getting the point. I am going to finish the example just for the sake of completeness, but it's always the same. Minus 1, minus 3, 1, 0, minus 1. Okay? So from this, we already have the first 2 layers. Okay? Now we continue with 0, 1, 2. 1, 2, 2, 1, 0, 0. And then 0 times 0, blah, blah. Okay, so always the same. 1 times minus 1 plus 2 times 4 plus 2 times minus 1 plus 1 times 0 plus 0 point minus 1 plus 0 times 0. Minus 1, minus 2, 2, 0, 0. Okay? Maybe I have made some fast mistake anyway. So you can see that from our convolution process, what we're getting is a smaller matrix than we had. We had a 5 times 5, and because we're padding with 1, and padding is 1, one step every time, and we are getting from a 5 by 5 with a kernel 3 times 3, a 3 times 3 matrix. Okay? No, it's not called padding, it's called stride, sorry, stride. The number of steps you take. Padding is something different. So this is convolution. This is what convolution is about. It's about multiplying matrices. That's why what we need for performing a good convolution is something called GPU, graphical process unit. Same thing that your PlayStation has. Because PlayStation games is just graphics. Moving graphics very fast, multiplying matrices very fast. A PlayStation is a GPU. And you can perform deep learning very fast with a GPU. So if your computer has a GPU, usually laptops, iPads don't have it, do not have GPU. They have a normal processing unit. A graphical processing unit is a chip that is designed to perform matrix calculations very effectively. Okay? So any questions so far?
We also have to do it with the green layer and the blue layer, or just with the...
You mean in the exam?
No, in the example we also have...
No, I finish here, okay? Of course, this is only the red convolution. You have to also do it with the green and with the blue. And then you get a 3x3 new cube, okay? New image. The result is this, okay? So what you get is something like this. If you use a filter that is aligned for this task, you do this, you get that, okay? So, but basically the way to think about it is first as an input of your, let's say, deep learning architecture, you have your original image. Okay. Then you have your, let's say, first convolution. Let's say this is a 3000 by 2000 pixels. Okay. So you have your first convolutional layer, something called convolutional layer, which does that, which we saw right now. Maybe it's you want to get the edges. Okay. You get the edges, and then you have your convolutional layer. Well, and this is an image that is also 3000 by 2000. Okay. Or no, maybe 1500 by 1000. Then you have another convolutional layer that gets the roughness of surface. And then you go down again in keeping just the most relevant information depending on the geometry of the kernel. So you're going down, and then you do your gradient descent back as we saw the other day. It's the way deep learning is going to work. I'll show you some examples later, okay? Now let's keep an eye on the concepts. So we saw the meaning of stride. Sorry about confusion. And now explain you the meaning of padding. So as you can imagine, if you use an edge kernel, or if you use an attention kernel like the one we have here, the information in the edges are going to get lost. And this is sometimes not very good, because you might want to catch some information that are in the edges, that you want to put your attention on that, right? So what you do is you do some padding. This means you add zeros around your image so that the convolution focuses on the edge, on the previous edges. Okay, so if you have your original red channel with padding equal 1, you get something like this: 1 1 0 2 0 2 0 3 3 0. I don't know, some numbers: 0 1 0 1 1 0 2 3 2 3 and 1 1 2 1 0. Okay, this is your original red channel, and you want to add some padding to it. A padding 1 would be something like this: 0 0 0 0 0 0 blah blah. Okay. So this is adding zeros. So this is padding equals 1 because we are only adding one layer, okay, of zeros, so that when we apply our kernel, we don't apply our attention kernel to this, we apply it to this. So now when we move it, shift it around, we are seeing in the middle of our attention the original edge. Okay? Okay? Does it make sense? So the first thing, we are seeing the edge always in the middle of our attention, or of our focus. And then on the second, we start doing the convolution as of the original image. Okay? So we don't lose any information when we do attention kernel. Okay? Make sense? Any questions?
Just general question regarding red channel. So are all these numbers value for red? So could they range from 0 to 255 or
Yes.
something else?
Yeah. All these numbers, but I'm not doing it with those because I don't want to multiply so much. I'm just showing you the concepts, okay? So wherever I say 1, 2, or 3, it can be any number between 0 and 255. Okay? Yeah.
We always apply padding because I mean it adds extra steps to our process.
No, only if you want to have that information in the edges.
Okay.
You can, you don't have to. Okay? So, any questions? Yeah.
Can the padding be higher than 1, or does it even make sense?
No, you can have padding of 20, but you will do a lot of calculations multiplied by 0. Okay, so you need to, always the padding is smaller than the size of your kernel, because at least you want your first run of the kernel to at least have some original information. Okay, so if your padding is 1, the minimum kernel you can have is 2 by 2, so that you at least get one part of the original information. If you have your padding of 3 and your kernel is 2 by 2, you start and you multiply only by zeros, and then you get nothing. Okay, so all these things are mixed up together in a way. Okay, so I have prepared for you some Python code or Python script. Before I share it, any questions on this? No? Good, then. I'll go on and stop sharing this. How do you do it? Stop sharing my iPad and start sharing my Google Chrome. So you see the those online see it, you don't see it here, so I need to put it on the screen. So this is I prepared for you this little Python code. Okay, it's a Python script. You can open it with Anaconda or something, whatever server you use for Python. Here, a couple things are explained. First, what TensorFlow is about, some background. Okay, those are the 3 channels, R, G, and B. Okay, and then there is some example for edge detection. So the first thing we do is we put the information in. Okay, so we have all the information, our 3 channels. This is a tensor 5 times 5 by 3, just like the image we saw, m times n times 3. Okay, in this case n equals m, so it's just a square, but yeah. So then we define our filter. For each channel you can define a filter, different filter. In this case, as I previously said, we have a very a kernel for edge detection in red, okay? A kernel for attention in the green. You see the same numbers that we used before, okay? A kernel for very strong attention in the blue. So the thing is, this thing is going to be detecting the edges in red, but very strongly the blue. It's going to filter out the blue. It's going to enforce the blue colors and the green colors. Okay, so we have 0 padding, and the stride is going to be 2, so 2 steps every time. And this is the way to perform what we just did manually. Okay, so the result is this matrix. This has done what we have done with our fingers and piece of paper. So this is the result of our convolution TensorFlow. That's the same, just way faster. It's a library to perform this sort of calculations. And there you have some references where you can read about convolutional layers, deep learning, and stuff. Okay? So if you are, I will upload it in a couple minutes. I think it's an interesting technology to get familiar with. Yeah.
I have a technical question regarding the technology behind. If we are able to calculate it by hand, why aren't then the so high requirements for RTX and so on if you want to digitize, for example, data?
Well, we can do it by hand because this is a very simple example.
Mm-hmm.
If you have an image like with 10 million pixels, you don't want to do it by hand. I don't think so. So I would be careful with that. No, I wouldn't start wanting to do it by hand in such a manner, I guess. So yeah, you can do it by hand, but I wouldn't do it. I wouldn't try. Just the computation requirements that you will need is would be so expensive. Would be so much that you wouldn't want to run it. So let me show you another example from.
So technically, if you would take only one part of an image and then try the calculation, it's not necessary to have high GPU power, right?
No. If you don't want to have all the image, if you just want to have one part and you know what part, you can. I mean, you can perform deep learning with your computer, no problem.
Mm-hmm.
It will run because Python is powerful and TensorFlow runs very well. You might have some problems installing TensorFlow or Keras in your new MacBooks because the chips they use, the M1 and M2, they are specifically made so that you need a GPU. Okay, so Apple guys are not very, they're smart. So this is for instance the thing that we were talking about. We can perform the. Let's load it. No, let's do it. Let me get the image from the repository so that you can see the effect. I just need to download it and put it on my desktop. And here, change this. Okay, so I'm gonna import the libraries. I hope it works. Didn't check it before. Okay, so no working. Wait, I need to install something. see if it works without. No, it doesn't let me. Let me check how to get it. The reason why it doesn't work is because Python is constantly updating, and it changes all the time. So this code ran last year, but this year doesn't run well. So, but anyway, I hope now it runs. Yeah, now it runs. So we get our filter described. So this is our image, okay? Just with these 255 numbers you wanted, okay? It's at 252 pixels times 257 pixels times 3. So it's a very small image. It's something that you would take with your iPhone 1, okay? And you would be very happy, but because you have an iPhone. I remember that time. So we define a filter. We say padding is 1. So after padding, the shape of the padding is 254 times 259. So we set the stride to 1, and we define the manual convolutional layer. What is saying they're going to broadcast together shapes? Okay. Stride 1. Padding 0. Okay, I need a little bit of time. Wait. Let me look why it's not working. I mean, it's super normal. The important thing is that you don't get nervous when you use Python. Just read the error and don't throw your computer out of the window. Just keep hanging in there until you fix it. Okay, so no problem. Even people myself that work with this shit like every day get issues. So just you see our filter filtered, highlighted the reds in the edges, highlighted the blue in the rest. Let's change the filter. So the filter is like this. So let's change it to highlight. Let's say now we want to highlight we're going to put the what we had as blue filter in the red and what we had as red filter in the blue. So what do you expect from here? Can somebody tell me?
To be red.
What?
To be red. No.
Red. See? See? No. It's getting my edges. Did it correctly? 0. It's because I didn't change anything. Just moved it. Very cool. So it did not work as expected. Why? So R is strong on the red. Let's put 0 here. Yeah, so now we lost the edges, okay? Because I put a 0 in the highlighting the greens, so we are only seeing the blue spectrum there. However, I would expect something different than this, and I would like to know why. Let's put here a 2, and here a 2. So it highlights nothing. B. Display 0. I'm gonna get zeros here. I'm gonna get an 8. No, we can play with this. Now we get yellows. Yellow is the combination of blue and green, right?
Yeah.
So why are we getting that? Oh yeah, because the red is being taken out. Okay, so it just shows it filters out the red, let's say. Okay. Yeah, so this is kind of the way these things work. You can have fun investigating, okay, testing different sizes. If you put here this is the size of a kernel, 3 times 3 times 3, so you go 3 times 3 and then on the 3 layers. Because it's not doing every layer every time, so it's multiplying all the whole cube, okay? The 3 layers at the same time, sorry. You can play with this a little bit. Important is that you understand point number 8. Okay, this is important for you for the exam. Okay? You can come and ask if you don't have experience with programming. I see some faces there. If you don't have experience with programming, no problem. Just come and ask. And say, hey, I don't understand this. Or I need help with that, and I will gladly explain. Okay? So, any questions so far? Then we hit a break. Okay? Stop the... we continue now with the K-means clustering algorithm, which is a clustering algorithm. So it builds groups out of data. Okay? The hypothesis is data are Euclidean. Because we're building a group based on distances. Okay? The K is a parameter giving the number of groups in which the data should be clustered. So the disadvantage of this method is that we need to tell the algorithm how many groups we want. This is sometimes it's easy because we know the data. We know it's women, men, children, old, whatever classes we want. But sometimes we don't know the data and we cannot decide, so we need to be iterative on that. Okay? So the advantage is this is fast and efficient. It's so fast and so efficient that we can do it with our pen. And I will definitely ask about this in the exam, so you want to try and do it and do some training before the exam. Okay, so let's look at the K-means algorithm. That's some steps, okay? So step 0. Decide, oh man. The number of clusters. I mean, intuitively, this would be K. Intuitively, let me paint a little drawing here to describe, okay? Imagine you have here two variables, and then you have like, this would be like a map, okay? And then you have a bunch of customers at this location, and then you have a bunch of customers at this location, and you have a bunch of customers in this location, okay? So you are Amazon, and you want to know how many groups you have, or who belongs to which group, to make sure you deliver to the one group with one supplier and so on, okay? So it is obvious, at least intuitively, that this group belongs together, right? This belongs together, this belongs together. So what this algorithm does is it helps us describe who belongs to which group in a very simple and efficient manner, okay? Given the data. We tell him we have 3 groups, but we don't know who belongs to who, okay? So let's see how we do it. We first decide how many groups we want to have. That's just the disadvantage, okay? We sometimes know, sometimes we don't. So step 1, distribute the data points in 3 groups. Okay? Or not in 3, in k groups, sorry. In k groups. So we just randomize. We say, okay, this data belong to 1, this data belong to 2, this data belong to 3. Then step 2, find the centroid of each group. Centroid is like the gravity center. Okay, it's a very simple calculation. It's just like calculating the mean value. Step 3, calculate the distance of the points to the centroids. Step 4, cluster the points by their distance to the centroids. Step 5, repeat from step 1 until the centroids are constant. Okay, so this, which seems very difficult. Oh my God. I cannot do it, I will not be able to do it. It's actually super simple as a pimple. Okay, let's look at an example. We have x, we have y, we have points who are 0, 3, b is 6, 1, z is 1, 2, d is 7, 0, and e is 2, 4. Okay, we can paint all this. X, y, 0, 3. This would be A. This would be somewhere C. This would be E. And this would be B and D, right? So somewhere here is B, and somewhere here is D. So intuitively, say we have two clusters. So step 0, sorry, is we have k equals 2. Then step 1, distribute the points into clusters. Let's take some clusters that are not real. A, B, and C. And 2 C and A, B, and C, and then 2 D and E. Why I say it's not real, because intuitively we would say this is the cluster, right? But I take this and I take this alphabetically. Just so that we train a little bit. So step 2, calculate the centroids. So the centroid of first group is 0 plus 6 plus 1 divided by 3, and 3 plus 1 plus 2 divided by 3. So I take that, just 0, 6, and 1 divided by 3. So this is the x coordinate, and 3, 2, and 1. 3, 1, and 2, the epsilon coordinate. So this is 2, 33, and 2. And the second centroid is 7 plus 2 divided by 2, and 0 plus 4 divided by 2. This goes all the way to 4.5, 2. Okay? So far, mean calculation is just super easy, right? So the third step is to calculate the distances of all the points to all centroids. So distance, I do the first, and then the rest you can, from point A to centroid 1, the coordinates of point 1 are 0, 3, so it's the square root of 0 minus 2.33 square plus 3 minus 2 square. Okay, so this is going to be 2.535. And the distance between A and Z2 is again square root of 0 minus 4.5 square plus 3 minus 2 square. Does anybody have a problem with this? Hello? Yes or no? Just calculating the distance between 2 points. It's should be straightforward shit, right? If it's not, tell me. The distance between A, because this is going to be asked in the exam, okay? I definitely going to ask this. So you need to do it, be able to do it in an agile manner. Distance between B and Z1 is 3.804, and between B and Z2, I already did this before, is 1.803. Of course, in the exam, you need to give me all the calculation, okay? Show me all the calculations, not just the number, because you can look left or right and copy that. So please give me all the calculations. I just do this here because I want to get more things explained. We have had a lot of holidays and stuff, okay? Calculating distances is not really business intelligence. So the distance between D and Z1 is 508, and then distance between D and Z2 equals 3.201, and then the distance between E and Z1 is 2.027. E and Z2 is equals 3.201. Okay, so now what do we do? Is there any question here?
I'm not sure if we will be able to calculate it by hand. Is it by using
Calculator.
calculator?
Yeah. You need to use a calculator, yeah.
Yeah.
Not with your hand, no. So if you have, let me do it because I'm not sure. If you have 0.1 and 0.2, okay? These are the coordinates. The distance between 1 and 2 equals x1 minus x2 square plus epsilon1 minus epsilon2 square. This is just straightforward from Pythagoras, okay? I mean, it's just 4th grade, I guess, or something. Or 5th. I don't know. So what do we do here? This is the key part, okay? This is the key step. We choose A to be in the group of centroid 1 because the distance to centroid 2 is bigger, 4.6. Okay? So we choose B to be in the group of centroid 2 and C in the group of centroid 1. And D in the group of centroid 2, and E in the group of centroid 1. Okay? So we have a new cluster. Step 4. New clusters are group 1. It's going to be A, Z, and E. Group 2 is going to be B and D. Okay? Which makes more sense from the data. B and D and okay?
Why A?
What?
Can you?
What was the question?
Why A? No. A, C, and E.
Because A, here 2.5 is smaller than 4.6.
Yeah.
And here 1.3 is smaller than 4.5, okay? And so on. So now we go back, because the clusters we have now are different than those that we hypothesized. We go back. We need to test it again, okay? So we go back to step 2. Or step, step 2. The new centroids. So this is 1 star. The new centroids are centroid 1 are the points 0 plus 1 plus 2. I take the coordinates x of A, C, and E divided by 3. So 0, 1, and 2, okay? And then the y coordinate is 3 plus 2 plus 4 divided by 3. This delivers a centroid situated in 1 and 3. And then centroid 2 star is 6 plus 7 divided by 2. The coordinates x of B and D, and 1 plus 0 divided by 2. And this gives 6.5, 0.5. Okay? So now we go and say, okay, step number 3. The distances between A and Z1 score is 1. The distance between A and Z2 star score is 6.96. The distance between B and Z1 score is 5.38. The distance between B and Z2 score is 0.71. The distance between Z and Z1 score is 1, and between Z and Z2 score is 5.70. Distance between D and Z1 score is 6.71. Distance between D and Z2 score is 0.71, and distance between E and Z1 score is 0.71, and between E and Z2 score is 5.70. So I choose group 1 for A, group 2 for B, group 1 for Z, group 2 for D, and group 1 for E. So the same groups that we had remains constant. The centroids are cool. We have found our groups. Okay?
How often do we have to do it? Only 2 times?
No, we do it until we find a solution.
Oh, okay.
Okay? Of course, if I give you 4 or 5 points, you can do it in 2 or 3 iterations. If I give you 2 million points, coming from 1 day of interactions in one factory, then enjoy. You never end. That's why we need such very efficient. So the clusters remain constant we can change. We can close the algorithm. The groups or the clusters are 1 A, C, E, and 2 B and D. In the exam, I will probably excuse me. Sorry. In the exam, I will probably tell you the first iteration needs to be with these groups. Okay? So that you have to iterate. And then the centroids, we have already calculated them, are Z1 star 1, 3, and Z2 star 6.5, 0.5. Okay? So this Cummings clustering, this is the way Cummings clustering works. It's very straightforward. It's just one line of code in Python. It's like the basics of the basics, but also very useful because you can use it to find the optimal logistics position of your supplier factory. Or if you're Amazon, you know where your customers are and how many products they want to have every week. You can locate your lockers optimally to minimize the distance. A bunch of problems can be solved with this very simple algorithm. Okay? So I give you one exercise. Could be something like this in the exam. Okay? The position of 7 factories with different demands on raw material, is given by their coordinates x and y in the map. Okay? Every factory is delivered by one of 2 suppliers. Okay? To reduce the transport cost the suppliers ask you to perform an analysis and recommend the optimal position of their supply points. Okay, so the data is given by X, Y, and the demand of each factory. Factory 1, position 1 to demand 2. Factory 2, position 2 to demand 1. Factory 3, 0, 1, demand 3. Factory 4, 6, 1, 1. Factory 5, 7, 2, 3. Factory 6, 3, 3, and 1. Okay? So now this is your task. But here, be careful, because you need to take into account something that we have not taken into account in the other problem, which is the demand. This means you need to be doing a weighted calculation of the centroids. Some factories have more than others. Okay? So there is a weighted calculation of the centroids. I leave you with a problem. Enjoy the problem. Okay? Oh my God. I have a bias. I have a bias. One, 0, 6, 7, and 3. And then 2, 1, 1, 2, 3. Two, 1, 3, 1, 3, 1. Okay? So I give you the first hint. If the first groups are 1, 2, and 3, or 1, 2, and 4, then the centroid 1 is 1 times 2, 1 times 2 for x, of course, plus 2 times 1 plus 6 times 1. It's weighted. The more demand, the bigger the point. Okay, so it needs to be weighted. Divide by 3. And then 3 times 2 plus 2 times 1 plus 1 times 1 divided by 3. Okay, so this is a hint. But do it yourselves. I strongly recommend that you do it. Okay? Questions?